moving on from the cyclic quadrilateral, which we just discussed in our last lesson, let's make one more observation. ABCD is a cyclic quadrilateral. If we extend the edge AB beyond the vertex, we create an exterior angle, this one here. This exterior angle and its corresponding interior angle will always add up to 180 degrees. That is the sum of angles in a straight line. But if you recall the previous theorem, adding the opposite angle on the interior angle also gives 180 degrees. So this exterior angle must be equal to the opposite interior angle, this one here. To render quantitative evidence to this claim, let's measure these two shaded angles and let's satisfy ourselves that they are indeed equal. Changing any of them will cause the other to change, such that they remain equal to each other at any point in time. Theorem: the exterior angle of a cyclic quadrilateral is equal to the opposite interior angle. Quite honestly, any question that requires this theorem can actually be answered with only the previous theorem on the opposite angles in a cyclic quadrilateral. But anyhow, now you have an extra tool in your toolbox of circle theorems. Example 10. If the angle at the center is 126 degrees, we need to half it to get this angle at the circumference. So, this interior angle at the circumference is equal to 63 degrees, which is half of the angle at the center. Therefore, x, the exterior angle, is 117 degrees to make a sum total of 180 degrees for angles in a straight line. Now, y is the opposite interior angle with respect to x. So, y is also equal to 117 degrees. Example 11. When we focus on this cyclic quadrilateral, x is the opposite interior angle with respect to this exterior angle, which is 77 degrees. So, x is equal to 77 degrees. We then shift our focus to the cyclic quadrilateral. Since angles x and y are opposite angles in a cyclic quadrilateral, their sum is 180 degrees. Therefore, y is equal to 180 minus x, which means y is equal to 103 degrees. A tangent to a circle is a straight line which touches the circle at only one point. AC is a tangent to this circle. This point, B, is called the point of contact. A tangent can only be drawn from a point outside the circle, that is, from an external point. The tangent never gets or passes inside the circle. Let us now draw a radius, starting at the point of contact. The radius and the tangent intersect at right angles, always. This is true no matter which side of the tangent you look at. Theorem: a tangent to a circle is perpendicular to the radius drawn from the point of contact. From the same external point A, we can draw a second tangent, AD, with D as its point of contact. Note that you cannot have more than two distinct tangents on the same point. If we now measure the distance from A to the points of contact of both tangents, what do we notice about the distances AB and AD? Quite clearly, AB is equal to AD. The lengths of tangents from the same point will always be equal. Theorem: the two tangents drawn from the same point outside the circle are always equal in length. The two main points to reiterate about tangents are: 1. A tangent and a radius always meet at right angles. 2. The two tangents drawn from a common point are equal in length. Another quick note: the quadrilateral OBAD formed by the two radii and the two tangents should look familiar. It is a kite, but that is not the focus of this lesson. Example 12. Line TO is the radius. The angle between the radius and the tangent is 90 degrees. So the angle OST must be equal to 39 degrees, so that the sum of the three angles in this triangle is 180 degrees. Example 13. The two tangents are equal in length, and so this triangle KLM is an isosceles triangle. Both base angles are 68 degrees each. So the apex angle X must be 44 degrees to make a sum of 180 degrees for this triangle. So X is equal to 44 degrees. Now let us focus on the quadrilateral KLOM. Each of these two angles between the tangents and the radii is a right angle. Angle Y plus angle X plus 90 plus 90 should be 360 degrees. That is the sum of angles in a quadrilateral. We know the other three except Y, and we can work out that Y is therefore 136 degrees. Here is a tangent to this circle. Let's draw a chord in the circle from the point of contact of the tangent. The angle between the tangent and the chord is this one here. It is important to note that this angle passes through one segment formed by the chord. The other segment, the shaded one, is called the alternate segment. If we shift our attention to the other angle made by the tangent, the alternate segment also shifts. The alternate segment is always the one which the angle does not pass through. Loosely speaking, it is always the segment away from the angle made between the chord and the tangent. Let's now subtend an angle from the chord into the alternate segment. Here, we are interested in these two angles, the one between the chord and the tangent, and the one in the alternate segment. To make our point, we need to take a measure of both angles. When we measure both, alas, they are equal. When we change one of them, the other one changes too, so that at any one time, these two angles will always be equal. Let's satisfy ourselves by subtending other angles in the alternate segment. This should eliminate all doubts about our initial observation. Any angle in the alternate segment has the same measure as the angle between the tangent and the chord. Theorem: the angle between a tangent and a chord drawn from the point of contact is equal to any angle in the alternate segment. Example 14. These two tangents and the chord define this isosceles triangle, and 52 degrees is the apex angle. Each of the base angles is therefore 64 degrees, so the sum of the angles in the triangle is 180 degrees. X must be 46 degrees, so that the sum of angles in this straight line is 180 degrees. To work out the angle Y, we need to recognize that it is in the alternate segment with respect to this angle 64 degrees. So y is also equal to 64 degrees. Example 15. Let's start with x. It is the angle between the tangent and the chord. And the angle in the alternate segment with respect to x is this 28 degrees. So x is also equal to 28 degrees. Before we find y, we need to recognize this right angle subtended by the diameter. Remember angle in a semicircle? X plus 90 plus y equals 180 degrees, that is, angles in a straight line. So y is equal to 62 degrees. We now need to observe that angle z is in the alternate segment with respect to y, so z must be equal to y, which must also be equal to 62 degrees.
Watch the next video. Share with a friend. Subscribe and hit the notification bell icon. Thank you for watching.